In section 10.5, we discuss the solid state of matter, and in particular, we talk about different ways of classifying solids. In a crystalline solid, the atoms or molecules that make up our sample are arranged in an orderly fashion called a crystal lattice. The type of crystal lattice that we have is based on or is named according to the type of particle that is repeating. So here's an example of the crystal that we see for copper. And what we see is it has copper atoms repeating in a regular pattern. This is actually called the face-centered cubic pattern, and you're going to learn about that in a little while. So copper, like many metallic elements, forms what we call an atomic crystalline solid because it is atoms that are the particle that is repeating in a regular style. Something like water, which is a molecular substance, obviously, forms what we call a molecular crystalline solid because what we observe are water molecules repeating in a regular repeating style. And what we notice with ice when it forms a crystalline solid is that we end up with a structure where every water molecule is maximizing its hydrogen bonding capacity, and that results in a structure that has a whole bunch of hexagonal holes all the way through it. And you might be able to see some of those hexagonal holes in the crystal structure of ice. So when the particle repeating regularly is an atom, we're going to describe our crystalline solid as being atomic. And when the particle that is repeating regularly is a molecule, we're going to describe our crystalline substance as being molecular crystalline. Now, ionic compounds also form crystalline solids. And in this case, the particles that are repeating regularly are cations and anions. And in particular, the ions are going to organize themselves to maximize attractions between oppositely charged ions, but minimize repulsions between like charged ions so that they actually, kind of hold together. But the important thing to realize is that in an ionic crystalline solid, it is ions that are the regularly repeating particle. There are some covalent compounds and non-metallic elements which form what we call covalent network solids. And what these are crystalline solids in which non-metal atoms are bound together in an extended network of covalent bonds. And you really just kind of need to memorize a few examples of these. I'm going to go through a couple of the more famous ones, and there are more listed in the book. So quartz, SiO2, is a covalent network solid. Every quartz atom is bound to 4 oxygen atoms in a tetrahedral fashion, and every oxygen atom is shared between 2 silicon atoms. So we have this array of covalent bonds that extends throughout the crystal. Carbon has 2 common naturally occurring what we call allotropes, different forms of the element. Famously, there is diamond, and in diamond, every carbon atom is sp3 hybridized and covalently bonded to 4 other carbon atoms. So that explains why diamond is harder than quartz, why a diamond can scratch a window, because in quartz, the oxygen atoms are only covalently bound to 2 silicons, whereas in diamond, every atom is bound to 4 other atoms. So it has more bonds, everything's bound in place more strongly, and so diamond is harder than quartz. The other common allotrope of carbon is graphite. And in graphite, the carbon atoms are sp2 hybridized, and they are covalently bound to 3 other carbon atoms in a trigonal planar arrangement. And then between, this results in layers of sort of like hexagons of the carbon. But then between these layers, we get weaker intermolecular forces. And so as a result, these layers can kind of slide past one another, which means that you can kind of cleave graphite. It also makes graphite slippery, which is why it is used as a lubricant. And then additionally, if you drag a piece of graphite across a surface like paper, then the graphite layer will have stronger intermolecular forces with the paper than what it does between the layers, and you can cleave off these layers. So that's kind of interesting. So we now have sort of a whole series of different types of crystals. When the particle that's repeating is an atom, we're going to call that atomic crystalline. When the particle repeating is a molecule, we're going to call that molecular crystalline. When we have a repeating pattern of cations and anions, we're going to call that an ionic crystalline substance. And when we have this extended network of covalent bonds, we're going to call that a covalent network solid. So just look at these 3 examples here. Look in the book, you'll see other examples of covalent network solids, and you'll kind of get a feel for how to recognize them. Now, not every solid is a crystal. There are what we call amorphous solids, in which the atoms that make up that substance are arranged in a disorderly or random fashion. So glass, window glass, is predominantly amorphous silica, has the same formula, the same ratio of atoms as crystalline quartz, but there's a random or at least semi-random arrangement of the atoms rather than a regularly repeating pattern of atoms. So in this structure, you'll just see that things are just disordered, right? They're not in a regular repeating pattern. So the crystalline structure of metals explains many of their properties. So copper, gold, and silver are well known for being quite soft and malleable. You can bend gold and silver and copper with your hands. It's why we like to make piping out of copper, because it's easy to bend around a corner. Now, this makes sense as to why copper would be easy to bend. Copper is composed of a bunch of atoms that are identical in size, that can be thought of as being like little spheres. And when we apply a force to the atoms that make up a copper crystal, these layers are able to easily slide past one another without in any way disrupting the bonding. So as a result, it's pretty easy to bend copper. Now, around about 5,500 years ago, it was found that if you add a tiny little bit of tin, or even quite a bit of tin, to copper, you get a material that is much, much harder than copper, called bronze. And bronze is also much, much harder than tin. And so this started what's called the Bronze Age, and we have a lot of Bronze Age artifacts, and it allowed people to do things like cast cannons, and you know, there was a big leap in technology associated with the discovery of bronze. So bronze is an example of what we call an alloy. And in an alloy, what we have is a host metal that you combine with one or more other elements. In the case of bronze, it's another metal, tin, but it doesn't have to be. In the case of steel, we take iron as the host and we add a little bit of carbon to it. Now, adding the other element, and sometimes there's multiple other elements that you add, can significantly alter the properties of the host. Bronze is an example of what they call a homogeneous alloy, where what happens is you take your copper, you take your tin, you melt it down, you give it a good stir, and you let it solidify. So what ends up happening is the tin is evenly but randomly distributed among the copper atoms. There are two ways of classifying alloys. One way is to classify alloys as what we call substitutional alloys. And in a substitutional alloy, what happens is atoms of the non-host element replace host atoms in the crystal. So that's what's happening in bronze. So what happens is we take out a copper and we replace it with a slightly larger tin. Now, for two metals to form a substitutional alloy, the atom that is substituting has to be within 15% of the atomic radii of the host. So what that means is if it's too big, it's just going to disrupt the bonding too much, or if it's too small, it's going to disrupt the bonding too much, and you won't be able to form a stable alloy. So in the case of tin, it's only slightly larger than copper, and so you can put up to 30% tin into copper and still form a stable alloy. So the question becomes, why is bronze so much harder than either tin or copper alone? Well, it's pretty simple. The slightly larger tin results in atomic scale bumps in the lattice. And when it's time for these layers to slide past one another, in order to get over the tin, a whole bunch of bonds have to be broken to allow it to get over the little bump. And that takes energy and makes it more difficult for one layer to slide past the other. So that's kind of cool, right? It's like a little molecular speed bump, and it creates a bit of an energy barrier to get over that because you have to lift up the whole layer in order to move it past the little bump. The second class of alloys are known as interstitial alloys. So what is happening in this case is that the non-host elements are occupying spaces, or what we call holes, in the host metal's lattice. So we're going to learn that there are different types of lattices, different types of crystal structures, but they all have holes or gaps in them. So this is that face-centered cubic structure that I was talking about that copper has, and you can see that there are these holes here halfway along each edge, and we could put a smaller atom in there, couldn't we? All right. This is another crystal structure. It's called a simple cubic, and you can see there's a very large hole right in the middle of that cube there, where we could put quite a large atom in there if we wanted to. So in an interstitial alloy, we aren't replacing a host atom with another kind of atom. What we're doing is we're putting an atom into the spaces in the crystal. Okay, so that concludes our brief introduction to the solid state of matter. I hope you found the video helpful.